4.3 is really just more practice using the ideas you learned in 4.1 and 4.2. And what we're going to try to do is sketch some graphs using the properties that we found from the calculus. So as you work through problems in 4.3, you should really just treat them as practice for the stuff that you've already learned in the previous sections. The first one I want to do, we're going to go all the way through and look at all the derivatives. And even the second one I'm going to do, we're going to look at all the derivatives. The last one is a rational function, and when you start looking at the first and second derivative, it gets really, really nasty. And I don't want to get too lost in the algebra. So for the last one, I'm just going to look at the first derivative. The first derivative is usually enough to draw the graph. The second derivative just helps you check the shape of your graph to make sure it's correct. So in all these problems, we're going to find the axis intercepts, and we're going to figure out the extreme values, the inflection points, where it's increasing, decreasing, all those things. And we start off with x to the fourth minus 6x squared. The first thing we find are the axis intercepts, and that's the x and y intercept. It's where we hit the x and y axis. To find the y-intercept, you set x equal to 0 to do that. And so when I put 0 in for x into my equation, I end up with 0 out for y. So the y-intercept turns out to be the point 0 for x, because that's what I plugged in, and 0 for y, because that's what I got out. If I want to find the x-intercepts, I set y equal to 0, and that's where f of x sits. X to the fourth minus 6x squared equals 0. I can factor out an x squared, and I'm left with x squared minus 6. So x squared equals 0 tells me x could be 0. X squared minus 6 equals 0 tells me x is the plus or minus square root of 6. So there are three x-intercepts. There's 0, 0, positive square root of 6, 0, and negative square root of 6, 0. So we found the axis intercepts from the function itself. To find the x-intercept, set y to 0. To find the y-intercept, set x to 0. Now I can figure out the critical points in increasing and decreasing by looking at the derivative. The derivative of my original function, x to the fourth minus 6x squared, the derivative is 4x cubed minus 12x. Now that's defined everywhere, so all I got to do is set it equal to 0 to find my critical points. I can factor out a 4x, and I'm left with x squared minus 3. So 4x equals 0, or x squared minus 3 equals 0. So one critical point is where x is equal to 0. The other two critical points are plus or minus square root of 3. Those are my critical points. I can find my extreme values by plugging those critical points into the original function, because the extreme value is just the y value that goes with it. Remember, y is x to the fourth minus 6x squared. The original one gives you my extreme value. When I plug 0 into x to the fourth minus 6x squared, I get y equals 0. When I plug negative 3, negative square root of 3, into x to the fourth minus 6x squared, I get negative 9. So let me double check that on the calculator here. Negative square root of 3 to the fourth minus 6 times negative square root of 3 squared. Yes, it gets me negative 9. And since every power is even, when I plug in the positive square root of 3, I'm going to get the exact same answer. Also negative 9. And so now I can figure out where it's increasing and decreasing by looking at a number line. 0, negative root 3, square root of 3. Those are my critical points. I'm going to test these into the first derivative, which is 4x cubed minus 12x. And so I'll pick some test points. Let's see, the square root of 3 is 1.7, I believe. Yeah, this is like negative 1.7. This is like 1.7. So I could put in negative 2, negative 1, a 1, and a 2. I'm going to plug those into the derivative. F prime of negative 2, 4 times negative 2 cubed, minus 12 times negative 4. That gives me a 16. That's positive. That's when I plug in negative 2. 4 times negative 2 cubed. Oh, I messed up there. 4 times negative 2 cubed minus 12 times negative 2. That gives me negative 8. Excuse me. When I plug in negative 2 into the derivative, the first derivative, I get negative 8. That tells me the function's decreasing there, because that's what I get when I plug it into the first derivative. I plug in negative 1 into the first derivative. When I replace all the negative 2's with negative 1's, the calculator gives me positive 8. So in this interval, the first derivative is positive and the graph is increasing. I plug 1 into my derivative. And when I replace all the negative 1's with 1's, I get a negative 8 out. So on this interval, the first derivative is negative and it's decreasing. And then I plug a positive 2 into the first derivative. I get positive 8 out. So I know it's increasing on that interval. And we can figure out what's local mins and local maxes. This is decreasing and increasing. So negative root 3 is a local min. This is increasing then decreasing. So 0 is a local max. The last one, decreasing then increasing. Positive square root of 3 is a local minimum as well from the first derivative test. And I know where it increases and decreases. It increases from negative root 3 to 0 and from root 3 to infinity. It decreases where the first derivative is negative, in this case negative infinity to negative root 3, and 0 to positive root 3. So we also know where it increases and decreases. Generally, this is enough to draw the graph. But we're going to go and look at the second derivative just to double check our concavity when we're done. 4x cubed minus 12x is the first derivative, so the second derivative is 12x squared minus 12. That's defined everywhere, so to find my inflection points, I have to set the second derivative, 12x squared minus 12, equal to 0. And I can factor out a 12, and I get x squared minus 1. And so I get x squared minus 1 is 0, x squared is 1, or x is the plus or minus square root of 1, which is plus or minus 1. Those are my inflection points. And I can check the concavity by plugging in test points into the second derivative. Notice plus or minus 1 are my inflection points. And I'm going to test around them, so maybe negative 2, 0, and 2. And I'm plugging them into the second derivative. When I plug in a negative 2, I get 12 times negative 2 squared minus 12. And that's a positive 36. The second derivative is positive, so it's concave up. Plug in 0 to my second derivative, I get negative 12. If the second derivative is negative, means it's concave down there. When I plug in positive 2, I get a positive number out of the second derivative. So I know that it's concave up there, so I also know where it's concave down and concave up. It's concave up from negative infinity to negative 1. And from 1 to infinity. And it's concave down between those from negative 1 to 1. So we found all the information they wanted us to find from the graph. We found the axis intercepts for the second, or from the original function, the critical points and the increasing, decreasing from the first derivative, inflection points and concavity from the second derivative. And so now we're going to put these together in a graph. So let's graph these. Now really you just need the intercepts of the axes and the first derivative to draw a graph. So that's all I'm really going to use here. I know that it hits the x-axis, or the y-axis is 0, 0, the x-axis is 0, 0, and plus or minus square root of 6. To figure out where the square root of 6 is, I'll type it into my calculator. It's 2.45. So the square root of 6 is almost at 2.5. Plus and minus square root of 6 are the x-intercepts. and 0, 0. So in red, I'm going to draw these x-intercepts on the graph. And it says that the critical points are at 0, negative root 3, and positive root 3. And root 3 is about 1.7. So look at where the critical points are. 0, 0 I already have on my graph as an intercept, an axis intercept. Negative root 3, negative 9, positive root 3, negative 9. So I'm going to put those places in. That's about 1.7. So here are my critical points. Negative root 3 and negative 9. Positive root 3 and negative 9. So they're in red right now. I'm going to put them in blue just so to note the difference. These blue ones are my critical points. And now I can draw the graph. I know that to the left of negative root 3, my first critical point, when I go to the left of that, negative infinity to negative root 3 means it's got to be decreasing. So this function has to be getting smaller and decreasing. Now between negative root 3 and 0, it says that my function is increasing between negative root 3 and 0. So that means I have to turn around and come back up to the 0, 0 mark. Now between 0 and the square root of 3, you'll notice my function is decreasing between 0 and root 3. So it turns around and moves down. And then from the square root of 3 on, notice my function is increasing from the square root of 3 to infinity. So the rest of this graph is just going to keep going up in this direction. So here's a pretty good sketch of f of x. Notice I didn't really need the second derivative. I really just used the first derivative to help me get the shape. I know this is root 3, negative 9. This is negative root 3, negative 9. This one is 0, 0. Root 6, 0. These are the x-intercepts. And you can use the second derivative to help you see how the concavity or something might be changing. I'll highlight this. You'll notice that this thing is concave down here where it's green. Or concave up where it's green, I'm sorry. Where it's green, it's a bowl shape pointing up. Where it's yellow, it's concave down. And if you'll notice, there are inflection points that seem to occur around plus or minus 1, where the bowl starts to change its shape. So this gives you a general idea of what the graph looks like. Notice we didn't really use the concavity except to check ourselves. And so that's the idea behind these problems that we're doing. We're going to find everything we can find from 4.1 and 4.2, and we're also going to find axis intercepts and use them to draw a picture of the graph. Let's look at another one. Here's another example that is a nice one to be able to work through. It's a weirdly shaped function, but it's x times the natural log of x. Now before we start this function, or this problem, I'd like to note the domain of the natural log of x. The natural log of x only makes sense for positive values. You can't put 0 or negative numbers in. So the interval that I'm really going to look at is from 0 to infinity, because none of the other ones will even give me a picture. And so if I want to find the axis intercepts, I can find the x and y axis intercepts. To find the y-axis intercept, I set 0 for x. Well, notice x equals 0 is not in my domain. When I put 0 for x, I have to take the natural log of 0, which is undefined. So since I can't get an answer out, there's no y-intercepts. To find the x-intercepts, I set y equal to 0. So I get L0 equals x ln of x. And so either x is 0 or the natural log of x is 0. Well, we can't have x equal to 0 because it's not in our domain. To solve the natural log of x equals 0, we have to put everything in the power of an e. E and natural log are inverses, so I just get x equals e to the 0, which is 1. So my x-intercept happens at 1, 0. So I found my axis intercepts by setting x and y together. Or by setting x and y equal to 0 in the original function. Well, now I can look for critical points by looking at the first derivative. So I take the derivative. Remember, my original function is x ln of x. if I want to take the derivative, I have to use the product rule because I'm multiplying two functions of x together. U will be x and the derivative is 1. V is the natural log of x, so the derivative is 1 over x. And so when I calculate the derivative, I use the product rule. I get u times v prime, x times 1 over x, times v times u prime, which is ln of x. So this simplifies into 1 plus the natural log of x. That's the first derivative. And just like before, this only makes sense when x is greater than 0. The whole problem is going to have that issue happening. So there's no place where this is undefined on the domain, so I can set it equal to 0 to find the critical point. So I get negative natural log of x equals negative 1. And just like before, I put them in powers of e. And so I get x equals e to the negative 1, which is 1 over e. So those are my critical points. The extreme value I get by plugging that into the original function. Remember, the original function is x ln of x. When I plug e to the negative 1 in there, for x, I get e to the negative 1 ln e to the negative 1, and I can use some log properties to write this as negative ln of e, and the natural log of e turns out to be the number 1. By the way, you could have typed this into your calculator, although it wouldn't have looked as nice. So I get negative e to the negative 1, which is negative 1 over e. So my critical point and my extreme value is 1 over e, negative 1 over e. And we can figure out where it's increasing and decreasing by looking at the first derivative on a number line. Remember, the first derivative is 1 plus the natural log of x. Our critical point is 1 over e. If I type 1 over e into a calculator to see where it lives, I get 0.37. So if I want to plug a number to the left to test it, I might test 0.25. Notice I can't put anything smaller than 0. I can't even include 0. So maybe 0.25 and maybe 1. When I plug 0.25 into there, I get 1 plus the natural log of 0.25, and that's negative 0.39. The first derivative is negative here, so it's decreasing. And I'm going to plug in 1 into my first derivative, and I get 1 plus the ln of 1. ln of 1 is 0, so that works out to be a positive 1. So I know from the first derivative test this is going to have to be a local minimum because it's decreasing and then increasing. I happen to know that it increases from 1 over e to infinity, and it decreases from 0 to 1 over e. This is enough to draw the graph. You know the intercepts, the critical points, and where it increases and decreases. I am going to look at the second derivative now, though, just so we can double check it with the concavity. Remember, the first derivative was 1 plus ln of x. The derivative of 1 is 0. The derivative of natural log is 1 over x. But remember, our x's have to be greater than 0 for this function to even have a picture. So remember, x has to be greater than 0. So to figure out where the inflection points are, well, there's one at x equals 0 because it's undefined at x equals 0. But notice I can't even use x equals 0 because I can only be bigger than 0. And if I try to set this thing equal to 0 and I multiply both sides by x, we have 1 equals 0, which doesn't give us any solutions. 0 times x is just 0. So there are no inflection points. We can figure out whether it's concave up or concave down by checking the second derivative. If I plug in a test point like 1 into the second derivative, I get 1 over 1, which is a positive 1. So it's concave up from 0 to infinity. And we don't even have a picture when it's less than 0, so I know the whole graph is concave up with no inflection point. So I'm going to put this together to draw a sketch of this graph. We know that at 1 over e, which is like 0.36, the y value is negative 1 over e. So that's my critical point. Let me draw it in blue. The critical point has coordinates 1 over e, negative 1 over e. And it has an x-intercept at 1, 0. And I know that at 0, this graph doesn't exist. And there are some properties that you're going to learn about in 4.7 where we can show that x ln of x, as x approaches 0, x ln of x goes to 0. So I know this graph is going to have an open circle at 0 there, but that's from stuff that we haven't learned yet. But if I've given you that, you can draw the rest of the graph because you know it decreases from 0 to 1 over e. So it's got to be getting smaller. But then from 1 over e to infinity, it has to increase, and it has to pass this 1, 0 point. So there's a graph of our f of x. Notice that's a local min where that critical point is. This graph is decreasing and increasing. The whole time, the graph has a concave up shape to it. So we were correct in our second derivative. So let me just look at one more problem. This last problem is a rational function, and these can get really messy to do. I just want to look at the first derivative and show you how it can give us an idea of what the graph looks like. So to find the axis intercepts, I'm going to do that first, and I'll show you the algebra behind that. The derivative I'm just going to write down, and you can double check me to make sure you get the same thing. So remember, if we want to find the y-intercept, we put in 0 for x, and we get 5. So we get 0, 5 out for the y-intercept. To find the x-intercepts, we set y equal to 0. But then I got to multiply both sides by x squared minus 1 to cancel it from the denominator. And so what really happens is I end up setting the top equal to 0. And so I get 5/3 as my x-intercept. Notice it's 5/3 for x, 0 for y, because I plugged in 0 for y to find it. Now if you want to find the derivative of this thing to find critical points, you can use the quotient rule, or if you rewrite it, you can use the product rule. When I found the derivative, I rewrote it that way and used the product rule. 3x minus 5 is u, and x squared minus 1 to the negative 1 is v. But I calculated that derivative, and when I calculated that derivative, what I ended up with is, oh wait, that's not f prime, that's f. But if I want to find f prime, I use the product rule. What I end up with for f prime is negative 6x squared plus 10x over x squared minus 1 squared plus 3 over x squared minus 1. That's what you get if you use the product rule on this function. And I can find a common denominator by multiplying the second term by x squared minus 1 over x squared minus 1. This is just so I can find a common denominator and add them together. And when I do that, I get a new form of this thing. This thing looks like negative 3x squared plus 10x minus 3 over x squared minus 1 squared. And just for complete clarity, you can factor this, and it's a little easier to plug things in if you factor it. So I'm going to write it in factored form. The top factors into negative 3x minus 1 times x minus 3 over x squared minus 1 squared. This is the easiest to work with. I had to do a lot of algebra to get there. But if I want to solve this equation, I can figure out, well, there's critical points where the x values, or where the first derivative is undefined. So I know right now I'm going to have critical points at x equals plus or minus 1. Those are vertical asymptotes, by the way, because it's where the denominator of this function is 0. This has vertical asymptotes, where x squared minus 1 is 0. So they happen at plus or minus 1. And that's why they're showing up at critical points here. The other critical points I find by setting the first derivative equal to 0. So I have negative 3x minus 1 times x minus 3 over x squared minus 1 squared equals 0. Again, we can clear the denominator by multiplying both sides by x squared minus 1 squared. And I get negative 3x minus 1 times x minus 3 equals 0. So 3x minus 1 is 0, or x minus 3 is 0. And so the last two critical points I get are 1/3 and 3. So I get some critical points. I have x equals negative 1 and x equals 1. Those are the vertical asymptotes where the derivative was undefined. I get x equals 1/3 and x equals 3. To find the extreme value, I plug it into the original function, 3x minus 5 over x squared minus 1. Well, when I put plus or minus 1 in there, since these are both vertical asymptotes, it's undefined y value. So there's no extreme value that goes with those. When I put 1/3 in there, so I'm going to plug that into the function. On the top I get a negative 4. On the bottom I get negative 8/9. So negative 4 divided by negative 8/9 gives me 9/2, or 4.5. The extreme value that goes with 3, on the top I get 4, on the bottom I get 8. So this gives me 1/2, or 0.5. So I found my critical points, my axis intercepts, my extreme values, and I can even figure out where it's increasing or decreasing, which is enough to really draw the graph for me. Here, the first derivative. If I write it in fancy form, where it's all factored out, it'll be easier for us to plug in to check it. Notice I have critical points at negative 1, 1/3, 1, and 3. So I'm going to test around these, maybe at negative 2, at 0, at 1/2, at 2, and at 4. And I'm going to be plugging these into the first derivative. Notice the bottom is always going to be positive because I'm squaring it. And a square is always positive, it's never negative. So the only thing I have to worry about is whether the top is positive or negative. When I take negative 2 and plug it in there, I get negative 6 minus 1 times negative 2 minus 3 over the number on the bottom is going to be positive. It actually works out to be 9. Well, this is negative 7 times negative 5 over 9. And there are 3 negative signs. So the overall answer will be negative. It's decreasing there. And then I plug in 0 into my first derivative. And I get negative 0 minus 1, 0 minus 3 over negative 1 squared, which is negative, negative 1, negative 3. Over 1, again there are 3 negative signs. So that means the answer will be negative in there as well. We can figure out the rest of the graph. We can plug in 1/2 into our first derivative, negative. That's 3/2 minus 1 and 1/2 minus 3 over the number on the bottom will be positive. This is going to be a positive number. This is going to be a negative number. So I'll have 2 negatives and a positive. That means I'll have a positive answer when I multiply them together. I can plug 2 into my first derivative. The bottom will be a positive number. 6 minus 1 and 2 minus 3. 6 minus 1 is positive, 2 minus 3 is negative. Again, I'm going to have two positives, or two negatives on top, which make a positive. And then I plug 4 into my first derivative. Negative, this is 12 minus 1, 4 minus 3, over 15 squared. This will be a positive, that'll be a positive, and there's a negative out front, so I get negative answers there. So I know where it's increasing and decreasing. Notice negative 1 and 1, nothing happens, but here at 1/3 it decreases and then increases. So 1/3 turns out to be a local min, and at 3 it increases and then decreases, so 3 is going to be a local max. So we can put this together to draw a graph of our function. We also know where it's increasing and decreasing. Increases, we can see from the plus and minuses, from 1/3 to 1, and from 1 to 3. And we know where it decreases. It decreases from negative infinity to negative 1, and from negative 1 to 1/3, and from 3 to infinity. And so now we can start to draw a picture of this thing. Now we have to know there's vertical asymptotes at plus or minus 1, and that comes from the x squared minus 1 in the denominator. We can find the x-intercepts and the y-intercepts from above. The y-intercept was 0, 5. The x-intercept was 5/3, 0. There's the y-intercept, 0, 5. 5/3 is 1 and 2/3. So here's our x-intercept, 5/3, 0. And then we know where our critical points are. At 1/3, we're at 4.5. So 1/3, 4.5. I'll put the critical points in as red. And another critical point at 3, 1/2. So the other critical point comes in at 3 and a positive 1/2. And so now I can draw a picture of this function. I know where this function is increasing and decreasing at, so I can use that to get the right picture. So if we take a look, we notice that there's no x-intercepts. From negative infinity to negative 1, it's a decreasing graph. So this graph doesn't have any x-intercepts out here, and it has to be getting smaller from negative infinity to negative 1. I couldn't have been decreasing above because it wouldn't have been able to cross the x-axis. Now in the middle it decreases from negative 1 to 1/3, but I have to hit these points. So there I am decreasing from negative 1 to 1/3. But then from 1/3 to 1 I have to turn around and increase. Notice since I'm following these vertical asymptotes I have to go up or down. Now from negative 1 to 1/3 I'm decreasing from negative 1 to 1/3. So that must mean that I'm coming down from negative 1 to 1/3, or I'm sorry, from negative 1, from 1 to 3, it increases, it says here, from 1 to 3. So this function has to slowly be getting bigger from 1 to 3 as it draws out here. So here's a picture of our f of x. Notice it's decreasing from negative infinity to negative 1, and from negative 1 to 1/3, and from 3, oh, I'm sorry, I have a mistake there. And it's also from 1 to 3, it's increasing, but from 3 to infinity, it has to start decreasing again. So this graph is slowly decreasing to its horizontal asymptote from 0 to 3. Let me put my critical point in here. It goes back down and gets closer to 0 again. So this critical point right here, which turns out to be a local max, is really hard to identify at 3, because, at least from the graph, because of the way the graph looks. But from calculus you can identify it. So you can see that it's decreasing from negative infinity to negative 1, from negative 1 to 1/3, and from 3 to infinity. It's increasing from 1/3 to 1, and from 1 to 3. So this graph matches the characteristics we needed.